Oh, right,
we got
yeah.
you.
Oh, we got it.
Smart, brilliant brains.
Yeah.
I want to say it was at like, I heard a story, it was either at like MIT or like. I don't know.
Oh, they were sick. Me.
And as
Me
a
too.
prank, like someone like went on the field, their football field, and wore striped shirt, you know, like a fucking referee, and fed the pigeons like every Saturday. Until football season happened, then he just kind of like sat back and waited. And all the pigeons thought they were gonna get fed by the referee.
That's amazing. Oh, that's incredible.
That's amazing.
Genius.
We'll get back on the officials.
That's awesome.
Oh my god, that's amazing. I love that.
Especially houses, you love the birds.
I do.
So if we
I
all
should-
just
I
have this belcher every day and start feeding the geese.
The geese will be.
Where did you buy
my
that?
servants? I will have an army of geese at my disposal.
You might need it someday.
Yeah.
Right?
I mean, with how your brain's looking.
I'll bring all my geese to the dean's office,
Yeah.
demand more money.
Yeah. What was that about not having another spot for tenure?
Yeah.
Budget issues?
Let's look at our office. We might just start getting ahead again. I think you guys are just gonna start
What
working
seems to happen?
and see where we go. It'll give us extra time to review or do other things. What are you guys feeling about stuff? Any questions? I mean, so last time we did gradients was like the, what'd you say?
Why is math notation so absurd?
I know.
We have to, like, we invent our own notation. Then it
What's
gets
up with this
reused and
derivative in
remodified.
the direction of you
I'm
having
talking
a
about-
D?
Like my discrete class, which is literally just your notation class.
Yeah.
I'm bored.
Well, the Ds are in
I'm
different
fine with the
geometries. We use the letter D as your general exterior derivative, which for Calc 3 is essentially the same as nav or del, I guess, which is just the operator of taking your partials. So sometimes you also write your partials like this. You don't have to write as much. Right? So mathematicians come up with notation that makes sense, and they get lazy at writing it, so they come up with different notation.
And then they get lazy for it.
Yeah, and today we're gonna talk about the Hessian, where second derivative. So, any questions before we get going? Everyone understand gradients? I think you guys picked it up naturally a bit last time. The gradient of a function will tell us our direction that we need to walk in for greatest descent. The magnitude of the gradient is the rate of change, or the greatest rate of change. And then if you have a level curve or a level surface, the gradient of the defining function will give you a normal vector to that surface. So kind of two different things, two different dimensionalities in regards to our gradient. And then so today, I think Alex was discovering that on Wednesday, that our other application of our gradient is going to be what happens at this point
But,
when we compute gradients.
let's say, that's the curve, right? And let's say that other side of that function goes like zoom.
Does what?
Goes up.
Zoom.
This
So
part
never
goes
stop.
up?
Yeah.
Yeah, goes it.
Goes to-
Then your absolute maximum of the entire function over the xy plane is like undefined, even though
Does
that
not
thing
exist.
exists.
No, this is a critical point. Well, so what's gonna happen with our gradient here? Gradient is 0. So if this is a function, z is equal to f of x, y. Our critical points are given function. The critical points are where the gradient of f. So what we have to do is learn how to classify them. And so Joanna was saying, well, if this thing goes zoom, then we're not gonna have an absolute max or an absolute min. Does anyone remember what the extreme value theorem is?
For any given domain, that like, it's a bounded domain, not infinite domain. There has to be in max and min.
Yes, so if f is a function of R into R. And actually here, call it, for lack of using these, call it from X to R, where X is, two things need to happen. It needs to be closed and bounded. And what?
X is a closed button flower that is simply waiting to open its petals to mathematical analysis.
Yes. Bounded and
That's Steven Strogatz or just?
No, that's just-
No, it's just a way to bring in that.
is continuous, then what do we get? Right, way too big. Then F attains max. And then fine. The two things, closed and bounded. In one, closed and bounded means that, well, we can't have an infinite one, but we also have to include the endpoints. So sets like 0 to finite set, finite interval, and it's closed. We include the endpoints. Though you could also have different copies of those. So you could have 0 to 5, but you could also have 7 to 10. So it could theoretically be disjoint if you really wanted to. We never went that far. So count 3, what's going to happen, especially if we are in R2. So if our domain is in R2, it just means it needs to be closed. So closed means we just contain the boundary. Moreover, it doesn't go off to infinite. Is what bound is. So examples. A lot of times we just write it in set notation. This is our circle of radius 4, including the interior, and the greater than or equals to tells us that we actually have to count this.
And that's just your range. That's not even the function we care about.
So this is the domain, yeah.
Hmm.
Yes, and so
That's just the domain.
just our domain, and then so other times they might just draw it, or they might do it as functions. Oftentimes they'll use like triangles and say, well, R is some region bounded by these lines, and maybe the first quadrant. So you know you have a boundary, and you know we're not going off to it. So that is our domain, which we're looking at this function. And so if we were to look at the function that I just drew, we were to have maybe a mound at one point, and over here we've got a saddle point. The other thing you would notice is that if I drew these correctly, at the critical points, our tangent plane is horizontal. Why is that? Our gradient is 0, why should the tangent plane be horizontal?
Tangent
Because
planes
that's
and
how.
direction.
Well, right, if we have, how would we find the normal vector to our tangent planes? If we have C is equal to f of x1. Create our level surface. This guy, right? Radiant of this guy is this guy will vanish for the gradient of that, fx and our fy.
How do we work uphill if there's no uphill? Or uphill is everywhere.
So if this was our function, the next thing we would want to add, if we are looking for absolute max and mins, we need to apply our extreme value. So we need our closed and bounded domains. Right now, as Joanna was pointing out, if this thing just goes, what was it, goes like yay? It goes like zoom, all the way up. Well, there's not gonna be an absolute max, and of course, on this left side, if we don't know what it's gonna do, it could go all the way down. And then there could be no absolute max. But as soon as we say restrict ourselves to the first quadrants over some box over our region R, well, what do we have to do? What was our process in Calc 1 for finding max and mins, absolute maxes and mins?
Just,
Test all the points and what else? Take derivatives, right? We always need to take a derivative, set it equal to 0. Find our local max and mins. In other words, find our critical points. We need to classify those critical points, or at least find the values of the function at that class, at those critical points. And then in Calc 1, what did we do? We checked the boundary points, because sometimes the function could be increasing really steeply at the boundary. And it might increase bigger than a local max or a local min. But we have a problem here in Calc 3. Because our region, our boundary of our region is a curve, right? It has infinitely many points on the boundary. And so we're going to have to come up with techniques for how do I check the boundary of this function and how do I check infinitely many points? There's two ways we're going to but first, let's get back to our derivatives. So that's going to be our process. Our first step, find our critical points. We need to learn how to classify the critical points. Then we're going to have to learn how to deal with the boundary. How do we classify critical points in Calc 1?
derivative 0.
Well, that's when we found the critical points. How do I tell if it's a local max or min?
So second derivative.
So you guys jumped ahead.
Or you could say when it changes from positive to negative.
Yeah, we could do these number line tests. So we find a critical point, and maybe we find plus minus.
That was so
we
bad.
say,
Say,
Were you?
I
It's
like,
like
I like
max.
did the second derivative test in order to figure out what I was going to put in the chart.
that would work. So this is another problem, is because we can't actually do this in Calc 3 because there's multi directions we can travel. And it could be increasing from one side, decreasing from another, and then we've seen our gradients and how to take directional derivatives in any combination of those. So what do we have to rely on? We can't do number line tests to use the second derivative.
Fantastic.
So how abstract do you guys want to do this?
yes.
Okay.
Yes.
So our derivative is really, it's actually the dual of the gradient. The dual of really the external derivative is just this operator that puts things in a matrix, or in a matrix of differentials or of derivative operators. So this is a column vector. Instead of writing it horizontally, we might write it as a column. And so what this is going to do when we apply it to F gives us exactly that. So whether you want to write it as a column or a row vector, we're applying these derivatives, so F gets applied in each coordinate.
That makes sense.
And so what do we need for our second derivative? We should be able to take another derivative of this guy. Our problem is that now we have three different functions. This is like F1, F2, and F3. So in our normal case, I'm taking a one-dimensional function or a one-dimensional output with multiple inputs. And when we take a derivative, well, since I have multiple inputs, I need the derivative of this one function with respect to each of those. We want to keep track of all of that Well, now if I want to take a second derivative, I gotta take derivatives of each of these guys, and each of these guys have to depend on potentially 2 or 3 variables. So let's actually do the 2 variable case just to save ourselves some writing. That, and I think most of the time when we use Lagrange multipliers, almost all the time it's 2 variables, so you can use it for 3. So now what we need to do is a notion of our second derivative. So we have all types of different first derivatives. Any directional derivative is a first derivative. But really what we want out of our first derivative for a multivariable function is this, because we want to keep track of, it encodes everything, right? This is the key for computing any directional derivative, is this guy, and then we just dot product with the direction. So this is sort of like our most general first derivative, but it changes the nature of the function, right? Our gradient not only has 2 input variables, but now it has 2 output variables. So now how do we take a derivative of this? It actually ends up being a matrix. So what we would do is we would take our derivatives, we would take our 2 functions. So if we write it in a column, so our gradient of f is df dx, df dy, or just fx fy. So these are our 2 new functions. Now, how would I take a derivative of this? It's essentially the same thing. If we kind of just look at fx, how do I take a derivative of this? Well, I need an x derivative and a y derivative. Exactly. So actually, maybe we do want column vectors. Oh, no, because each of these are different functions. Exactly. So what we want to do is then create a matrix. So our second derivative is going to be, let's see, we want to write it as an operator. Because our output should be a 2 by 2. So we want operator. I think we want this as a column and the other one as a row. Yeah. So what we want is now this derivative operator, dx and dy, acting on. No, I'm doing this back. Actually, we want a 2 by 1. So d, yeah, you guys will get to enjoy all of this once you get to linear algebra, making sure your matrices and your vectors are oriented correctly. So this is our derivative operator. We now act on this guy. You guys know how to do matrix multiplication? Man, high school is failing. In high
It's
school,
just
like, I learned
matrix.
how to do, I mean, just a general public school education, had to do matrix multiplication and determinants before college, before even high school. I think we did it like maybe late middle school or early high school, some random algebra stuff.
They took that out of algebra too, I think.
I think we did it, but it was like maybe a week.
Yeah,
My teacher mentioned determinants once because it was cool, and I remembered it because it was cool.
So this is a 2 by 1 matrix times a 1 by 2 matrix. So it's
So
always
it's
row
a 2
column.
by 2.
So it becomes a 2 by 2. And how do we find our 2 by 2? Position 1, it's like doing the inner product. So it's going to be this row inner product with the first column. Nicely enough, we just have 1 entry by 1 entry. So we'll have ddx of fx gives us fx. In the 1, 2 entry, we do this first row, second column. So it'll be
Oh,
fy,
like
or I
the,
guess fyx. But for posterity. And then so our second row, first column is going to be our second row dot product with the first column. And we will have y. And then of course our last one, second row, second column. Gives us that y. Now, this is what we would call the second derivative.
The third derivative, just a bigger matrix, or is it a 3D matrix?
Good question. This is what I was hoping for.
I don't like that.
also, is that D like a normal D, or is it like a weird fancy D?
Regular D, regular capital D. fancy like calligraphy Ds are usually for a domain.
Okay.
Capital regular D is derivative. Multi-dimensions, yes. Okay, so let's take a look at something. What's our Taylor series?
X of AB times.
Oh,
We love binomial expansion.
We do. So one way we could write this. This is just the gradient of that dot product with our directional vector. Why is this a directional vector?
Oh, God, you're right.
It is the change in X
oh,
and the change in Y.
oh, no.
Oh, yes.
Oh, no.
So if you consider this
I actually
as-
like this much better.
So our f gradient of f is in vector form, is fx, fy. So our dot product is just this guy, this row by this column gives us our dot product. What do you
But
think the
instead
next
of writing it in linear form, you write it in less than form.
What?
In this form.
Yes. Yeah.
And
Oh, in the angle brackets?
confuse yourself with orientation.
Yeah.
Like when you're looking at your phone in bed and it changes direction if you don't want to.
Yeah.
So,
You don't want the math.
Our question is, what's the next term gonna be?
G, derivative of the gradient
So this is
times.
our df, or if you wanna
Oh.
call it as our first
Oh.
derivative. So our zeroth order term, our second or first order term times our change in x or change in position. Plus, what do you think the next one is?
It's that one.
Yeah.
We should have this guy, but we run into a little bit of a problem. So just to
No.
review, let's explain it and see what happens. Why? What is a vector? When a vector acts on another vector, we usually have these dot products. That gives us a scalar value. We need scalar functions.
But there's like 4 things in that matrix.
Yeah, but there's too many things in this matrix, so how do we resolve that?
Two of them are the same thing.
Yeah.
Because if we have this guy, we're gonna get really close. Let's see what happens. If we have this matrix acting on this vector, then what are we gonna get? We are going to get a new vector. This is going to be fxx times x minus n plus fxy. Y minus b. Right, first row, first column gives us our first entry here. Now our second row, first column gives us 2, 1 entry. So it's going to be fxy. Say, plus y. And our problem is this is a vector. All know the Taylor series formula now, and it shouldn't be a vector, it should be a scalar value function. How do you think we resolve it? What's our problem with the order of magnitude here?
That's weird.
We're still linear, right? In our change in x and change in y, we're still linear. So what we actually have to do is we want this to be a quadratic term. So we can't square a vector, but what we can do is actually multiply on the other side.
Oh,
So we still need to include that there. Let's,
that fixes all the problems.
and that'll fix everything. So
Why?
I don't know.
Because-
let me erase here a little bit. It's the
Are you saying because you also don't
matrix
understand or because you do?
Yes. No.
x minus a, y minus. So if you want to put a comma here and use your angle brackets, you can. So now if I'm acting as a 1 by 2 matrix with a 2 by 1 matrix, we'll get a 1 by 1 matrix. our scaling. So what happens if I take this term product vertically? We get x times x minus a. We will have fxy, or sorry, this guy times this guy, so fxy times x minus a. And y minus b. And then we will have, sorry, this one should be squared. And then we'll have this guy times our bottom row, which will give us another fxy term here. So we'll have two of those. And then plus our. So. This is our tail. So the question is, now what do we do for the third?
Use a computer.
Actually, that's not far off. We would use Maple or something. So after you, matrices are a subset of what are called tensors. So this is the 2 by 2, or a matrix is a 2 tensor.
Oh, have you looked into TensorFlow yet? For your AI stuff, machine learning stuff? It's very good.
So in order to find the third derivative, you probably need a 3 tensor. And that's going to be beyond anything we can get into.
So yes, three-dimensional essentially.
It's essentially a 3 by 3 or 3 by 3 by 3, or yeah, 3-dimensional matrix.
Yes,
A
okay.
cube-
In some
A
sense.
cube with numbers in it.
Yes.
It's a cube number. So along these lines, I'll leave it to you guys. One way you can simplify this just by writing the delta x as a transpose.
What's the
So
delta
if you
x?
have, so this is our vector. Normally, like we have x and y, but oftentimes it's x1 and x2.
Oh,
X3,
okay,
x4,
okay.
so sometimes we just use x vector or delta x vector. And then the transpose just means take a column and make a row.
Yeah.
So you usually write as delta x transpose times delta x on the other side. Okay, so using this, you can actually begin to show of how we classify critical points.
Yes.
So we have gradient of f at AB. We know we have a critical. So our information as to whether this critical point is a local max, local min, or saddle point has to come from this second derivative. And our second derivative test you guys know how to, what do you guys write?
I'm taking notes.
Chase its own.
Those are beautiful notes. Holy crud.
I don't know how to do that.
Wow.
I don't know what I did. I think you can work your data.
So what is the determinant of the matrix? Do you guys know how to compute that?
Didn't I have to do that for one other thing that was a lot easier? than
Cross
this?
products.
Yeah.
Oh.
Cross product. So for a 2 by 2 matrix, we just take the product of the diagonals minus the product of the anti. This is called our Hessian matrix. The determinant of that gives us our second derivative.
How do you spell the Hessian?
HESSIAN.
Is it the same thing as like the Hessian people?
That George Washington hired?
No. Oh, yeah, those
Some
guys.
mercenaries? Maybe, I think so. I
Well,
don't know how many of
actually,
the
wait,
Hessians
those
there
guys
were.
were German, right? I think. Well, I mean, they were Hessians, obviously, but like, From the German period.
George Washington hired Germans to win the war.
Yeah, they were like,
Was it
okay,
George Washington or
fun
was it
story.
the British?
No, like the Hessians were like for hired
Like
mercenaries.
German badass motherfuckers.
Yeah.
That's awesome.
Okay, so this is our star.
The beginning of the American military industrial complex.
If star is greater than 0. And let's say it's greater than 0. Then AB.
So say FYY is easier to compute.
Also valid.
Okay.
So this is what's part 2. And that's less than 0. Then our usual second derivative. So essentially what this means, I mean, fxx and fyy you can interpret as you would our normal first derivatives or second derivatives in Calc 1. So fxx is like the concavity of our curve in our x direction. So this is essentially saying like the concavity in our x direction is positive. But because our function can rotate, there are all sorts of things between its increasing and decreasing as we rotate our directional derivatives, we still need this to be positive. In some sense, another way you can kind of think about it is, if you think about it, this is the product of our two directions, or fxx and fyy. This is kind of giving us the rate of change of the slope as we rotate around. Like if you take the x derivative, that's our slope in the x direction. Then if we start to change in our y direction, we're rotating. So in some sense, if this is positive, it's saying that this quantity is bigger than this. In other words, even though our slope might change as we change from x to y, it's not changing enough to dominate over the primary
So
concavity.
if it's
Does that make
going
sense?
like if you're here and then you rotate it and your slope goes like that,
Yeah.
then maybe it'd be negative.
So it's like the slope in the x direction could be increasing. And then as we change in the y direction, it's just increasing steeper or maybe less steep. And then so what's the point going to be? It'll still be a concavity or a maximum. Whereas if our Hessian, our determinant of the Hessian is less than 0, then we get a saddle. Essentially, it means that I have one change in the x direction, then as we're rotating, well, our change in the first derivative in the y direction is actually dominating. So we're changing rapidly, and then now all of a sudden I'm going from increasing the x and then now decreasing the y. Back. So we might have this. If you want a more rigorous or more mathematically analytical way to do it, it all comes from this. And trying to think that if this matches those sides, then you can estimate bounds for your delta x's and delta y's where all of that should up. So if you're interested, I would suggest looking it up. It's kind of an interesting read. I think some of you guys would find it accessible. So. Any questions? Let's actually do examples. We actually need to get to classifying or to finding the boundaries. Can I erase all this?
If equal to 0 does not ever occur.
Inconclusive. It's like our second derivative test. And Calc 1, the second derivative is 0 at the same time the first derivative is 0. You can't tell.
Wait,
So it could just mean anything.
Could be a saddle, could be a max, could be a min.
do you know the same thing as star?
Sorry, d squared. It's
Also, wait,
same.
It's all
That's
the
what we
same.
should really call this is magnitude.
That's a
we just called it
label.
star- We just called it star because that's more fun.
I just call it star just to reference it, not to rewrite it, but technically, I guess it is, so this is our d squared f. And then so the magnitude is the determinant. The determinant of a matrix is equivalent to the magnitude of a vector in some sense.
So that
This is
star
notion of
isn't a
theory.
variable, it's just like.
It's just a
vector.
reference. This is like equation star.
So we
If
could
equation
like,
star is greater than 0.
It's a name, it's a name, it's
it
a
could be
label,
a
it's not
happy
actually.
face. it
Yeah,
could be
sorry,
a
that was
spiral.
confusing.
That was very
Not a
good, and I
variable.
was really afraid that everyone else knew what you were talking about, so I didn't ask.
Yeah, just a reference, because I ran out of room writing. Wanted to reference it.
It's a label, not a variable.
Yes.
We are not introducing simple variables.
Yes.
Ah, yes, if you take the star operator. thing,
There are
which is the-
star operators. Some of you
That's
guys
why
are
I was so
musical.
confused.
Since some of you guys are musical, there's flat and sharp operators.
No.
Then there's like the natural, yeah,
Yep.
Wait,
there's
So they're
some,
on-
and indifferential geometry. they call
Any simple you can imagine, math has appropriated it for something.
it. Pretty much.
Dang.
Example. Critical points. Define and classify critical points. For. Y equals to 1/3 x squared plus minus x minus. Mary Beth likes to use a lot of the same functions, because she finds good ones. And then, actually, was this on the video? I don't actually check. all
This
the-
was in lecture today.
All the preview assignments, were you?
We have.
We took a party.
We took
Yeah.
a party. We like going to 2 lectures. It's fun.
Good, yeah. Well, so you guys have already seen all this stuff.
Yeah, no, not this
Not this
stuff.
stuff.
This stuff is interesting, that's why we go to both.
Because like, I feel like Maribeth's lecture is like, right, this is how you do it.
This is
And then your
just-
lecture is like, so this is why it's interesting and cool and why you should care.
Yeah.
Yes, I would agree with that.
Yeah, no, Mary Beth, well, 'cause she's gonna train the average. She's gonna train the average engineer. Most engineers, it's like, how do I do things?
Give me
Not
the equation
necessarily-
that I can do the thing with.
Why it's interesting, they need to know how to use everything. So all the examples, most of the examples I pulled from her notes. So if you've seen it, they're gonna be repetitive. So where are our critical points? Let's compute our gradients. So we'll have x squared plus 2x minus 1 plus 3y minus 2y. And then our y derivative 2y minus 2x. So our critical points are where the gradient is 0, specifically the 0 vector. Each coordinate needs to be 0. So x squared plus 2x minus 1 minus 2y equals 0. And then y minus 2x equals 0. Solve them however you would. Y equals x. These ones are linear equations. They're not always linear equations. So substitutions can work best. Y equals x. And then, so minus 2x, we just have x squared minus 1. Plus or minus 1. And then y is that corresponding value. So our critical points are 1, 1, and so how do we classify them? We need to compute our second derivative, so our fxx.
Don't we need to do star first?
Do what?
Don't we need to compute star first?
Well, star has these parts in it. So I'm
Oh,
doing, I always do
okay.
it in pieces. We can write out, I mean, it's fxx, fyy minus everything. So we're computing that, but it's so much easier to do in pieces, especially if you've got finite space. 2x plus 2 fyy is to 2, and then fxy is negative. So nicely enough, it's not too bad. And then so our star equation determinant of our Hessian matrix. 2x plus 2 times 2 minus negative. Sometimes just from the second derivative, it'll pop out, especially if the second derivative actually doesn't depend on x. So 4x plus 4 minus 4. And now we would plug in our points. So at 1, or sometimes we just write it as d squared, but more appropriately, the second derivative of that term. Gives 4, which of course is positive. So what's that tell us? X. Is 4, also positive. So, local. Then minus 1 our tension is negative 4. Less than 0, so it's a saddle.
What about a relative minimum and saddle point?
This is a great question. At 1, if let's say x equals a is only critical value and that is a local minimum and absolute and global. Nice theorem, especially if you're trying to shortcut a lot of Calc 1 problems. If you know you found one local minimum, it has to be the absolute. You don't have to look for other ones. Do you guys think this theorem is going to hold in Calc 3? If we have one critical point, it is a local minimum. Is it the absolute? Why not?
Because we saw this in
Oh, you cheaters.
I wanted to see what Beckett thought before you spoke, but
Well, I don't think so. No.
Yeah, crazy stuff can happen in Calc 3. Because as soon as you have
Because you can be doing
directions,
this in one dimension and this in the other dimension. And that's the only critical point.
you can have a local minimum, but then like the function, it doesn't even have to be a saddle. It can taper off in one direction, whereas it's not, like the derivative is never vanishing. So it could decrease, but then the other sides, like let's say it's a straight line in and
they
out.
don't curve up.
Yeah, they don't curve. So maybe in the X direction, it curves down and there's like a local max looking like there is one in the X direction. But in the Y direction, it's just a straight line going downward. And so there's no zero gradient. Even though we have a local max. Yeah. I know. It's crazy.
Bumpy functions goes in.
Bumpy functions. Okay, so if you guys have already seen this, we should do hard stuff then. Right? Is that what you just said?
As long as you can like stop the algebra, once it gets like, okay,
The rest is easy.
So not all of you guys saw Mary Beth's.
No,
Yeah.
only
So we should.
go.
Okay, so let's try to find the absolute. Yeah, fine. Well, we can go later if you guys want to stick around, or if you guys.
I have an exam, so I can't.
I have a bus.
We've got a function, z is equal to x squared plus y squared over a region R. Bounded by y equals 2 minus. So z equals x squared plus y squared, what's that look like? Yes, exactly. It's a bowl parabola. And then so if we were to plot this, y equals x, and y equals 2 minus x squared. 1, 2. And I missed something. Which one did Mary Beth do? This one or this one? Should either say the y-axis or x-axis. Which ones do you guys want to do?
The what? I'm confused, like,
So here's our plane. We got y, x, and then we've got the line y equals x. Maybe we'll draw it slightly vertical. This is the line y equals x. 2 minus x squared. Y. So it's kind of this upside down parabola.
oh,
And you always got to be careful with these regions. This is actually a big point of people losing points on midterms, is understanding which box.
She didn't bound it by either. She went on the other side, the negative axis.
Oh, okay.
Yeah.
And then so in that, we've got this z is equal to x squared. So this picture is going to be hard to draw, especially with this back face. So we've got this parabola sort of sitting the sun behind everything. And then the line y equals x is going to go back on the xy plane. Then to follow all of that, we've got our pole. And so we want to find the max min values. What do we have to do? First step is to find our local max min. So gradient of z, x dy, 0, xy. So do that, do your second derivative, classify it, they have a rule, find. So now the question is what to do about the boundary. And maybe we can try to draw that picture. Let's draw a y horizontal. We've got y equals x. We've got that. So what you want to think about is the boundary of these paths are going to lift to a curve on our function.
Projected onto the curve.
Exactly. And unfortunately, it's going to be really hard to draw unless you're a good artist. We're projecting this curve onto our function. Exactly. So what we have to do is try to understand, well, where on this curve do I reach the highest point, the lowest? Yeah.
to electric boogaloo.
Slow head nod. It's like a slow clap, but
Oh, it's
for
just like
students understanding things.
visualizations of functions.
So we found the minimum on the interior. Now we actually just need to find the boundary. And unfortunately, our boundary has two pieces. It has the parabola part and the line part. So we do have to do this in two parts. So check boundaries. There's two ways. We either parameterize do count, and then two, we can do Lagrange multiplication. which we will do on Monday. So, that can feel about parameters.
I can do it.
We've got f of x y is what, x squared plus y. If we are on our parabola, you can essentially take that as our parameterization. If you really want to use t's, you can. Or you just plug that in and you apply it. So your f of t on this part of the curve, that's part, which is going to be t squared minus t squared. How do we find the max mins? T equals 0 and how do we check the ends? What do I mean by that? Yeah, because on this parabola, we have this point and this point. Luckily, we only have to check them once. If we check them with the parabola, we won't have to check it again for the line. But we might find the local max somewhere over here on the parabola when it comes up. The mins could be at these points. So how do we find those? We would have to find the t values corresponding to when those mixed up. Yeah, you guys with me?
Yeah.
You guys want to see it, more work to do, or are you guys comfortable doing it? I want to shortcut you guys if you guys want
I think this is also an like a video example on a preview.
to. Okay,
You can watch again.
yeah. I mean, I'm happy to go through if you guys want, but we are running out of time. If you guys also want to stay on that, I'm happy to do that as well.
I have place to be.
Cool.
Have fun.
All right, so we will end it there. We can see another example on Monday as well, and then do Lagrange multipliers, which are fun.
Some pictures about it.
Have a good weekend, everyone.